it says recording, so ergo it's recording.
Okay, alright, well, so to recap, in the abstract, all these different nodes, right, we got 3 different nodes, and I'm basically discussing, like, software-wise, code-wise, how do these things be, how are we implementing these things. So there's master node, there's delegate, let me do witness actually first. This guy will be this guy, dub, and delegate. Okay, so these nodes need to talk to each other in pretty complex ways. They need to have a different messaging pattern set up for this guy to talk to this guy without this guy knowing of all the different master nodes and all the different witnesses. Ergo, the necessity for some kind of architecture that basically encapsulates not only should the behavior of these nodes, like how should they behave when they receive messages from different nodes, but also how should these nodes hook up and how should they actually talk to each other. Not what should they do once they hear something from someone, but how should they actually talk to each other. So that's another complexity kind of baked into this architecture. And that being said, I guess let me get right into it. So the actual business logic for all these different nodes is implemented using a state machine, right? The basic task of a node is to take in some input, some message from the outside world, and perform some behavior as a function of that input and his current state. And this is more complicated than in a traditional database setting because each node essentially has to be autonomous. They can't really trust anyone. You know, I can't trust any of you guys. If I was a node in this system that I'm describing here, right? So I basically have to validate anything that you guys tell me. I have to fact check it to make sure that that's a sane thing to do. I'm never going to kind of just blindly, listen to anyone else. So that being said, all I'm basically getting at is the business logic for this is kind of complex, which kind of stipulates the necessity for a state machine to organize all of that logic, okay? So that's that. That's the state machine. That's kind of where the business logic lives. So let me draw that over here. State machine. And just to kind of give you a basic idea of what a state machine might look like Master right now has a pretty simple state machine where he really just has 2 states, I think. He just has a boot state. And when he's in the boot state, he goes and he connects to all the different things he needs to connect to, and he updates himself if he's been offline for a while, etc., etc. And then he has a run state, where he's actually open to receiving messages from the outside world, and he's processing them, and he's kind of working at full capacity. So he's pretty simple for master node. So we got boot state. And the states are much more complex for nodes like, in particular, delegate, because delegate has to do consensus and lots of other stuff. But we're sticking with the simple example right here. So boot state, run state. You start at boot state, this is the entry point to the system, and you go into run state, and you pretty much chill in run state. Okay, so that's the business logic, like I said. Now let me kind of describe the architecture of how we interface with the network, how we interface with other nodes.
So question, you're looking at this from like the network perspective, right? So,
yeah, I'm talking about everything, just kind of.
Yeah, well what I mean is like boot state is going to accept the transactional input and probably ignore it, right?
Yes.
Okay, so like the ports are always open and the state machine is dictating how input is handled.
Yes,
right? Okay.
yes. Well, I mean, this boot state actually opens the port. So it's possible between the time that he opened the port to the time he's transitioning here that he'll receive transactions.
Sure, of course.
In which case he doesn't handle them in the same way as he would in run state. He basically like puts them to the side and is like, hey, I'm not ready for these yet. Once I get to run state, all these transactions that I got while I was in boot state, let me actually go ahead and do big boy things with them.
Yeah.
So maybe stupid question, but is there a queue for that?
Yes, there's a queue. You're exactly right, there's a queue. So yeah, anyway. So the Reactor architecture is basically our implementation of event-driven ZNQ non-blocking asynchronous server. Okay. So yeah, what you've all been waiting for. It's finally here. Anyway, so basically the idea with that is we want a very lightweight way to receive connections from multiple endpoints on multiple different servers without basically having to do any kind of like nasty while loops or any kind of unsavory computer science constructs that require heavy context switching or blocking behavior or anything like that. This is a very, very lightweight architecture. It uses file system handlers, SIG handlers, and all that under the hood. And I think it uses MQ select, I think, is the actual Linux kernel command, I think, under the hood that the Reactor is using to wait for different sockets to be written to and stuff like that. And basically he kind of organizes all of these different file handlers for all these different network sockets that he has going on. You know, these might be all the different peers that he's connected to. He has a different file handler for each one. And he kind of funnels them into this central interface which can receive the messages and then pipe them over to the state machine who will actually process them. Okay, so I'm not going to get into like the actual ZMQ patterns right now, but if you'll just entertain me, like let's just say we have some different kind of socket types. Like we have a deal socket. This is kind of like for requesting. There's a route socket. And then there's a sub socket, pub sub socket.
So, are you assuming this is just for the messages that we've dictated? Because essentially there's a finite amount of transactional inputs, right? Mm-hmm. You're like, oh, someone sends a post request to a master node and then it gets propagated. Pub sub, right? Mm-hmm. But that's not what this really is, because we're assuming that we're going to put an overlay network over everything, right? Mm-hmm. Is that, well, how do those two paradigms fit? Like, why have a reactor? Why not just pub sub it and call it a day?
Right, so the reactor basically provides us an API for hooking up arguably complex communication protocols between different nodes. So with PubSub, basically, we're in a situation where we're always shouting. Whenever I have something to say, I shout to all you guys, and you can kind of choose your ears and not listen to it. But at the end of the day, I am shouting. The message is being transmitted on the wire to you, and you're just choosing not to do anything with it. So if we kind of were just to PubSub everything, it would be very, very wasteful, because there's many situations where we just want to have like a one-to-one connection. Like maybe Falcon is a master node, and I just want to ask him stuff, and he wants to reply to stuff. In that context, it wouldn't make sense for me to publish to all master nodes, or similarly for him to publish to all delegates, when really we just want to talk to each other. So building these kind of complex communication protocols, I guess I'd say, these kind of communication patterns, I guess is probably a better way to put it. We don't want to put in here, we want to put in here. So this guy kind of handles the complexities of how do you talk to other people. So does that kind of answer what you're getting at, or not really?
Yeah, I think so. I'm just trying to like ask you questions so that it like opens up more understanding, right? And so, does that make sense?
Yeah, I think it supports concurrency more.
Yeah.
More fluently than this.
Yeah.
Kind of also, this is a side note, but like what Davis and I have been talking about regarding this is that it potentially opens up a lot more use cases. Like right now, it might not make sense in the system that we're creating. In terms of like the reactor probably isn't being utilized to its highest capacity. But when we have a overlay system that's a peer-to-peer system, you're going to have to deal and route messages that may not potentially pertain to you, right? Yeah. And so like you do these hops. So like one particular node hops to another particular node, even though that message is being published across the entire network, it's simply routing it across. And so that's when this reactor makes sense, because you open a deal route port and you're just like, look, if I get any messages, I'm just going to forward it to this thing. And that's generally how you do like a peer-to-peer network. So like right now, we're just assuming that, all messages go to all witnesses and then they publish them to delegates. But in a system that scales to like 1,000 different witnesses,
yeah,
you know, a master node publishes one transaction to 1,000 witnesses. You just have 1,000 messages and you have a million packets flying around. It
Yeah.
doesn't make any sense.
Yeah, that's it. That's a really good point. And I think another kind of inspiration for this design decision, I guess, is really to kind of build an SDK
Yeah.
and to allow
Yeah,
other
yeah,
people to write on top of it.
Yeah.
So let me just jump back to the state machine real quick. As a state machine, basically, all you kind of have to worry about is, what kind of message did I receive, and who do I want to send it to? Do I want to send it to another witness? Do I want to send it to the master node? Whatever. You don't worry about how that happens, how it gets there, how the message gets routed, or any of that kind of stuff. All you define is who do I want to talk to, and how do I want to behave when I talk to them. So it very nicely encapsulates the business logic here and the kind of networking stuff here. Okay, so there's actually something in between these two layers, and there's not really a name for it, but I'm calling it the routing. Okay. And let me also draw the different procs. So this entire business here, the reactor, he lives in his own process. And basically right now, the routing and the state machine lives in a separate process. So this is actually the main process. Let me call this proc 2. Okay, so basically what the router does is it listens to all these receive events that this reactor might get. Say the reactor gets a message in from the web. And it basically feeds it into this separate process using a ZMQ pair socket. So this is a one-to-one relationship between these two processes. And the router will actually dispatch that message to whatever the current state machine. Sorry, let me back up. It will basically figure out, okay, what is the current state of the state machine, and what logic should be used to handle this message? What behavior should be implemented? And kind of like we were saying earlier, for example, when you're in boot state and say you're master node, and you're in boot state and you get a transaction, you're not really ready to broadcast that to the network yet, so you might add it into the queue. So the router basically figures out, okay, he's in boot state. We want to run this method with this message that we received, namely adding it to a queue. But if you're in run state, there's a different implementation for receiving a transaction. If you're in run state, you actually want to maybe broadcast that to all the witnesses, or you want to check the proof of work and broadcast it or whatever, right? So the router basically figures out, okay, how do I dispatch this message that I just got onto the appropriate business logic inside the state machine. And the routing also handles signature validation, does checks for data integrity, basic checksums and things like that, and basically aims to make sure that once the message actually gets to this point, it's good. Like we shouldn't have to do any checks for signing. We shouldn't have to check if the thing is actually deserializable or anything like that. As a node, when you receive a message, you just trust that this back-end architecture has done the magic to ensure that that message is valid and ready for processing.
So you're not going to run into like errors when you actually do it.
Do what?
Like you do your processing, you're not going to run into errors because it would have caught it at the router. That's what you're saying.
Well, it depends what kind of errors. Like, maybe a transaction doesn't. Maybe this is like delegate.
Mm-hmm.
Okay? And you got a transaction. Falcon is trying to send Daniel 20 coin, but Falcon doesn't have enough money.
Mm-hmm.
Right? That's not going to get caught in the router.
Yeah.
That's actually going to have to be interpreted inside the state machine before you're like, oh no, this transaction is not good.
Right.
But if Falcon submits a transaction and the proof of work is bad, or the signature is bad,
Yeah.
or he's tampered with the bit padding or something and try and inject some kind of malicious, seg faults or whatever, that's going to get caught before it gets to the state machine.
Right.
So kind of like these more low-level primitive checks
Yeah.
about data integrity and such will
Yeah.
get performed in this layer, and also code signing and
Cool.
signature validation will get performed in this layer.
And the ZMQ pair is inner process.
Yeah, ZMQ. So ZMQ pair is basically like the pattern we're using to communicate between these two processes. It's kind of like having like a queue or something. Yeah, go ahead.
Question. So there are boot state and run state. What about for errors? Like, are there also dependent like tasks that may like you like, oh, you need to. It might be just a ledger where you like do transactions, right?
Mm-hmm.
But like, aren't there business processes where like one has to happen before the other, and then you have to make sure.
So sort of like a Markov chain, like the state machine, and you can only be in one state at a time.
Mhm.
Is sort of like the key idea. So this is the more simple state, like for the delegate state machine is really more complicated.
Oh.
And I don't know, you're talking about like passing things around between state, but it can only be in one state.
Yeah, it can only be in one state at one given time.
Okay.
So like, I don't know, maybe it'll be helpful for me to just draw a more complicated state machine.
Mm.
So let's draw a delegate, for example, now. Okay, so like the other ones, he starts in boot. He moves to interpreting state. Interpreting basically means it's kind of like the equivalent of run state. He's receiving transactions from the network, and he's executing them against his own state, and basically updating his own state. So, I'm getting in, Falcon gives Stu $5. Let me update Falcon's balance to -5, and let me increment Stu balance by 5. All that kind of stuff happens in interpreting state.
Is this answering your question, or
Yeah, or am I going off track?
Well, no, I was just wondering because the way that I heard it was that, like, let's say 2 transactions come in, how are they ordered? Is that more of your question, or are they answering it?
That's one thing, and the other thing is like, so you're trying to do enterprises, right? So there would be like things that are not transactions. Right?
Such as.
Smart contracts, you mean? Like that sort of thing?
Yeah, maybe.
That's what he's trying to say, right?
Yeah,
I think so. Like you're trying to, like a transaction, there's 2 types of transactions. A transaction, you think it's an exchange of something, right? Or you're sending something to somebody and the balance is being deducted. But when we say transaction, we mean a non-revertible, in a very, it's an atomic process that happens.
Yeah.
So like you could say, like for example, registering a piece of data on the chain, right? That's not a transaction in typical sense, but it's still a transaction. Does that make sense?
So in the network level, it is still a transaction.
Yeah. So we're calling them all transactions, even though like what I'm trying to do is take this whole pattern that Davis has made and then basically incorporate that into the interpreter on a level such that it feels like you're just initiating method calls, right? So you're like send X coin to this person, and then it's a transaction, right? But so much so that it feels like you're just executing a command.
Okay.
Is that
I'll try to find like use cases later, maybe.
Okay.
Possibly. Kind of
Okay.
build into this.
Okay.
Yeah, I mean, this is pretty much from a high level what it looks like right now. The actual mechanics of how we do the routing, how this works, is a little bit trickier. But from a high level, this is what's going on. I don't think it's really that complicated from a high level. Yeah, is there any questions? You want me to finish up drawing the state machine for delegate?
Yeah, show us a complex one.
All right, so this is not even that complex, but this is more complex. So boot state, and then we go into interpreting state. Okay. We're in interpreting state for a while. Either we stay there if our time is if we're not done interpreting, or we can transition into consensus state. Now, right now, our consensus implementation is pretty simple. So it basically lives in one state. But in the future, as our as our consensus algorithm kind becomes more full, a little bit thicker, it might make sense to have sub-states on top of consensus. So, I might be in consensus state, and within consensus state, I'm on like round 1, or, I'm in the point where I'm building a Merkle tree.
Right.
There could be many, many sub-states within consensus, but for now, conceptually, let's just say consensus is one state.
Mm-hmm.
So you're in consensus. Either you're chilling there if you're not done yet, or if you're done, either you were in consensus, you were successful in consensus, or you were unsuccessful in consensus. Either way, you're going to enter updating state. And how you actually update will be very different depending on if you're in or out of consensus. So updating might have a possible substate. It might be like, okay, fetching from master node, or it could just be copying scratch to state. Okay, so it's updating. From updating, it can be one of these states, and then there's a couple things that happen in between, but TLDR, then it goes back to interpreting state. So this is the simplified view of delegate to state machine.
So we're basically saying a unit in time, kind of like the classic, like, what is that thing? Like everyone says a state machine, and then they have like a turn style thing, like the entrance where it clicks, you know what I'm saying? Like every unit by which the state could change is initiated by some sort of transaction, right?
Yes.
In the network.
Yes.
It's not like it's mutating in real time. There has to be a transaction that causes it to change.
Yes and no.
In a way, maybe I should say
In
like
most cases, yes. In
Okay.
most cases, in each state, you're basically chilling there, and you are receiving messages from the outside world, and those messages will influence how you go about these different states, right? So let's take consensus for an example. You're in consensus, which I can't spell, and you're basically checking your work with everyone else in the network to see if you guys have the same answers for the test, okay? And you're going to be receiving like signatures from other people, and the way you handle that is going to be different than the way you would handle them if you're interpreting, right? If you're interpreting, you're not ready for consensus, so you're basically just stuffing these signatures into internal queue, and then once you're here, you're actually executing them. So when a message comes in, it basically gets routed to one of these guys, whatever the current state is, and then one of these guys, basically one of these states, will specify what should we do with that message, how should we behave, and that behavior I'm describing can either be a transition to another state, a composition of a message to another node, or both. So yeah, to answer your question,
that input from the reactor is
what makes these state machines transition.
It's like a gumball machine. You got to do an action, and it's not going to spit out a gumball until some action's being taken.
Exactly.
That action's always from the reactor.
Exactly.
Okay, cool.
Exactly. So yeah,